In this question, they are asking to give the IUPAC name and electronic configuration of central metal atom in terms of T2G and EG of, here a coordination compound is given, that is K4MnCN 6 times. Okay. So first of all, we are going to give the IUPAC name of the compound. This is from the topic coordination chemistry. So here we are going to write the name. We are starting from the cationic part, that is potassium. So the name is potassium. Now we are moving to the coordination sphere, that is the ligand should be named first. So we are writing potassium, 6 ligands are there. So hexacyano. Now here manganese, that is the metal, is a part of negatively charged coordination sphere. So the name should end with 8. So potassium hexacyano manganate. Now we have to write the oxidation state of that metal. So I am taking that oxidation state as X. Now the charge of this complex ion will be -4 because we have 4 potassium outside the coordination sphere. 1 potassium have 1 plus charge, so total charge will be 4 plus. So the coordination sphere have a charge -4. Now X plus 6 into -1, that is 1 Cn minus have a charge of -1. So X plus 6 into -1 is equal to -4. So X is equal to -4 plus 6, that is +2. So the oxidation state of manganese will be 2 here. Okay, so the name is potassium hexacyanomanganate 2. Now we have to write the electronic configuration in terms of T2G EG configuration. So here we have to write that manganese is the central metal atom and the oxidation state of manganese we got it as Mn2 plus. Normally manganese have the configuration 3d5 4s2 and Mn2 plus ion have the configuration 3d5. In terms of T2G EG configuration, you can write T2G5 EG0. Now the second part of this question, what do you mean by chelate effect? Give one example. Okay, so chelate effect means we can see in case of bidentate ligand. If a bidentate ligand is making bond with the particular metal atom, they can form ring structures by donating more than one pair of electron. So they will be highly stable and the complex we are getting is called chelates, and the stability can be improved by this chelate formation. That particular property is called chelate effect. So that is chelating effect and chelates. Now write the hybridization and magnetic characters of the following complexes. First one is given as FeCN64-. Okay, so the first compound is FeCN64-. So I am starting from the central atom, that is iron, have electronic configuration 3d6 4s2. So here iron, what is the oxidation state of iron? That will be, I am taking as X. X plus 6 into -1 is equal to -4. So X will be +2. So Fe2 plus have the configuration 3d6. Now in 3d6, if you draw the box diagram, the electronic configuration will be 1, 2, 3, 4, 5 and 6 electrons will be like this. Okay, so here Cn minus is a strong field ligand. So when the Cn minus is attacking this iron, the electrons of this iron gets paired. So this electron will pair like this. So the electronic configuration will become all the electrons gets paired. So 1, 2, 3, 4, 5, 6. So here we cannot see unpaired electron. It means this FeCN6O- is diamagnetic in nature. So when the Cn minus ions are coming, 6 ligands are there. So we need 6 vacant d orbital, but d orbitals are not there. So we need 6 orbital vacant. So we will use 2 3d orbitals and 1 4s orbital and 3 4p orbital. So the hybridization is d2sp3 hybridization. Now the second compound COF63-. So the same way we are calculating the oxidation state here. So here it is 3-. I am taking cobalt as X. X plus 6 into -1. 1 fluorine have a charge -1. that is equal to minus 3. So x minus 6 equal to minus 3. X is equal to plus 3. So in case of cobalt, cobalt 3 plus have the configuration. Before that, cobalt have the configuration 3d7 4s2 and cobalt 3 plus have 3d6 configuration. So they will be like the d orbitals. So 1, 2, 3, 4, 5, 6 electrons. And now we are checking the strength of the ligand, that is fluorine is a weak field ligand. There is no pairing of electron. So we have to use 1 4s orbital, 3 4p orbital and 2 4d orbital for bonding. So the hybridization will be sp3d2 hybridization, and here you can see 3 unpaired electrons. So they are paramagnetic in nature. Now the third compound, that is NiCO4. So here the complex is chargeless. So the oxidation state of X, that is nickel, I am taking as X. Now X plus carbonyl group is 0. So 4 into 0 is equal to 0 means X equal to 0 for this NiCO4. So the electronic configuration of nickel, that is 3d8 4s2. In the complex itself they are in the same form. Now we are writing the box diagram. So here 1, 2, 3, 4, 5, 6, 7, 8 and 4s orbital have 2 electrons. Now we have to check the strength of the ligand. The ligand is carbonyl group. Carbonyl group is a strong ligand, so the electron will pair up. So the 4s electrons will move back and all the electrons in the 3d orbitals gets paired up. So it will be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 4s orbital is free. 4 carbonyl groups are there means we need 4 vacant orbitals, but here only 1 4s orbital is there. So we need 3 orbitals from 4p. So the hybridization is sp3 hybridization. So in complex you cannot see any of the unpaired electrons, means they are diamagnetic in nature. So the first compound is D2sp3 hybridized and they are diamagnetic, and the second one is sp3d2, that is the outer orbital complex with paramagnetic property, and the third one is sp3 hybridized with diamagnetic property.